So more metric spaces. The last definition was just an illustration of what we can do with the metric spaces, how far we can go. So once again, I'm not going to go all the way to topology, but this part is very foundational for topology, and then you might probably think of a few examples of topological theorems in calculus. So functions, the only thing that is involved is the only requirement from a function is continuity. Okay, so not differentiability. There are no derivatives. There are no integration. Nothing like that. So well, I wonder if you remember any theorems from calculus about continuous functions.
Intermediate value theorem?
Yes. Okay. Intermediate value theorem. Okay. What is it?
That's the theorem that the slope between two.
No, that is the mean value theorem. The intermediate value theorem. Anyone? The mean is so the value is that so sort of averaging is what the mean value theorem is about. The intermediate value theorem is, well, let me try to make a picture for you like this. A continuous function, so it doesn't have to be differentiable. Does it look familiar just yet? Okay, so intermediate, what intermediate, in what sense intermediate? I mean, the name has actually, sometimes theorems have nothing, their names have nothing to do with the what's going on. This one does. Intermediate value theorem. Intermediate, what does it mean? It means that it lies between the values, between the other values that we know.
Doesn't it say that like a value between 2 points, like a function, if the function is continuous,
Yeah.
from one point to another, then there's a value for every
Yeah.
x in the domain between.
For every y. For every x, it is the definition. It is the definition that for every x on between a and b, there is a value. That's simply a function, right? So there is a, if you go from x like this, you will always find a counterpart. Okay, so that is simply, it's called being a function. Okay, this is the opposite, intermediate, you go backwards. Will you always find a value, corresponding value for this way, like this, from y to x, and that is the intermediate. Y is intermediate between f of a and f of b. Okay, so f is continuous on ab. Okay, and y is any value between f of a and f of b. Then there is an x in AB such that f of a is equal to f of x is equal to y. Okay. So once again, going from x to y from x to f of x, it doesn't really tell us a lot. It is just a function. Any function has that. Going backwards, it's easy to miss a value. So just here's how we miss a value. Okay. Try to go backwards. If I pick this value y, I will not find a corresponding value of x. Okay. So why? Well, because the function is discontinuous, right? So there. So that's the intermediate value theorem. And so once again, nothing but continuity, except the only thing that, so it is naturally stated for the real numbers. We're not talking about functions in general. We're talking about the values of the function. The domain is reals or an interval, and the codomain is also reals or a subset of it. So we can't figure out, this one is easy, but what we can do what does it mean to be, can we make y y-axis or codomain to be a vector space. I'm sorry, not a metric space. And the answer is not quite because why? Because of the word between. There is no such thing as between in a general abstract metric space. The only we got a set in distances. How do you say that you have 2 points in a metric space? What does it mean for something to be between them? There is really no such thing, strictly speaking. Well, you probably might try to work something out, but it's certainly not anywhere on the surface. Okay, so but at least there is no trouble with the well, there is some issue of what to do about the there's a possibility that we can do something about the x-axis or the codomain. So we could try to generalize this theorem by making the x-axis to be the domain to be a metric space. So suppose we have a continuous function on a metric space. Is there some kind of from reals to from some metric space to the reals? Okay, and then between makes sense. And is there an analog of the intermediate value theorem? And yes, there is. There is just x has to be something more than just a metric space. Not every metric space now works. So let's try this. So try this in what sense? Is there an intermediate value theorem? So is there intermediate value theorem from a metric space to the reals? So the y-axis is still there, but the x-axis could be anything. It could be a line, real line. It could be plane, a multidimensional space. Could be metric. Could be taxometric. Could be a sphere. So does it make any sense for the intermediate value theorem to exist in this general setting? So, yeah?
They're still continuous, like surfaces, right? Like if it's a plane, it's still like a continuous surface.
Right. Well, you I think you're thinking about the graph of the function. So, and then, well, certainly it would be worthwhile to take a look at a few examples of what can work out. So, suppose this is my domain. So, function x is R2. Okay, so what do you think? So the trouble with this idea is that once again the problem is what does it mean for a value to be in between the two values, and there is no there is once again there's once we move from an interval to abstract metric space, then there is no such thing as the endpoints, and therefore there is no f of a f of b, the endpoints. So we cannot ask the question, is there a value between f of a and f of b, because there is no a and b. Such as, for example, I pick a square on the plane. Suppose this is my domain. Whatever the function is, it might be some kind of surface, right, like this, maybe. Okay, above the square. So function of two variables. It might be continuous. Remember calculus 3. So then you cannot say there is no n and b. So what do you think? What would be the meaning of the intermediate value theory? Well, let me give you a hint, and the hint is what is the image, or the range, if you prefer. What is the intermediate value theorem tell you about the image of the interval? So this is the question: what is f of AB? this is the image or the range, if you prefer. Well, what do you think the range is? You consider, just look at the example. What's the range? The picture on the right, on top. What's the range? The image. Oh, you take all the x's between a and b. That's the domain, and take them and look where the function takes them. This is my domain. What's the range? In this particular example, yeah. So then this will be the range. The point is, it's an interval. An interval, as opposed to, which is the point I would like to make, is that as opposed to the case when the function is not continuous, then the image is, look at it. It's made of two pieces. So that is actually the topological discovery that the topological description that you have for a continuous function under this theorem, that if the function is continuous, then the image is an interval, and when it is not, it might not be an interval. In the sense, not just not an interval, it might have a gap in it, intermediate values missing. That is the gap, and that is the term that we use, and you probably saw it in calculus theory. The term is with or without a gap. What is it called? A set. So I'm not talking about functions, I'm talking about sets. So that interval in two sets in yellow. One is an interval, and the other one is two intervals. What's the term to describe the one piece set? Calculus 3, remember? Maybe. When you study multidimensional spaces, then some sets things become more complicated in dimension 1, and you describe sets, and you actually describe things such as open sets, closed sets, so we will get to that later, but one even more crucial thing is what? They're called connected. So that's the difference between those two sets, is that this one is connected, and this one is not connected, or disconnected. So once again, that's the where topology goes from where we are now, is studying connectivity, and that's the continuity is sort of, in a way, is something that put on top of it, is that the continuous connected goes to connected. Look at on the continuous function, connected interval ends up with a connected interval. Okay, so the image becomes of connected is connected. However, if the function is not continuous, then the image might not be connected anymore. Okay, so that is literally discontinuity. So what does this function do as a transformation? The first one, I mean, it does something. I mean, imagine that you have a piece of wire, and that's your interval, and then what does the continuous function do? Well, there's some wild stuff. It might be even to do like this. Okay, so we're not require differentiability, so it could be anything. However, imagine now discontinuous function. It does this. It breaks it. So that is really discontinuity. Not just little pictures there, but if you think of functions as transformations, and that is probably a good idea once you go to high dimensions, that these pictures don't help anymore. So you think of functions as transformations of you transform the domain into the codomain, and then what is so special about continuous functions? They do not make breaks. They don't break. They stretch, bend, fold, flip, whatever, twist, all of that, but they do not break. So that is the perfect example when you see a break. In fact, well, maybe using a yellow here is kind of a misleading. So this is the image, okay, and this is the other image. So the green interval is transformed by the first function into another green interval. Okay, so even though you can see folding there, right? You can see folding, you can see stretching, all of that is happening, but there are no breaks. It does not break it. The second one does. It creates a gap in it. And that's the meaning of the intermediate value theorem, kind of interpreted in a more topological way. And then once you understand that we are talking about connectivity, then you can move on to higher dimensions, including the abstract spaces. But if we just take that example at the bottom about two-dimensional situation, so then you have a connected set, such as a square, and its image will be, once again, a connected subset of the z-axis, which is what? Once again, probably an integral. So if this is my domain, then codomain will be here somewhere. So that's what a function of two variables does. It takes the domain transform, which is in the xy plane, it takes it to the codomain, which is the z-axis, and then it might be, once again, if its function is continuous, it will be another integral. Okay? And then as you go high dimensions, then that certainly will be, well, more complicated, but let me give you one more example. It is, so this one is from x to r, I'm sorry, from r2 to x. This is what this example gives us, from r2 to r. Now, if I take example from r to r2, remember this is, what is this? From calculus 3, what do we call these functions? From r to r2? What its graph, what is kind of graph, is what's its image. So I have a surface over there, the graph of that function of two variables, what should I draw here? What kind of object? A curve. I'm talking about parametric curves. So something like this. Doesn't matter what it is, but it might behave wildly. But the domain is here. It may be an integral, maybe the whole thing. That doesn't matter. And then the codomain is in the xy plane, and then it could be, say, maybe, why not a circle? Say. So that's what it can do. It take an integral and it bends. It can glue. So if you think about this as a transformation, then there could be, just as that folding over there, you can put things together. It does not have to be one-to-one or onto. That has nothing to do with it, but it is not allowed to break. So I could take that line over there, the x-axis of my parametric curve, and then I could do anything I want with it, as long as it's end up on the xy plane, or rather on that vertical plane. And it could be a circle, could be a spiral, anything like that. And once again, the idea is that that curve will be continuous, and that's how we explain continuity of curves in high-dimensional spaces, by saying that they are parametrized by a function which is continuous. Okay. So then all of them have this analog of intermediate value theorem. You don't say it that way anymore, because between is gone, and you have to deal with more higher level concepts, topological concepts, and that concept is continuity. So in fact, let me define this for you, if you don't remember from calculus 3. So suppose XD is a metric space. So a subset A in X is called path connected. If there is a continuous function f from integral AB to A, I'm sorry, yeah, I jumped, yeah. Path connected, which means that any 2 points can be connected by a path. So that is a very, very simple idea. I have point A here, point B there. In my okay, let's decapitalize this. A and B. This is my A, a subset of X, and then what I'm saying is that there's a curve between them. Okay, so once again, if for any 2 points, for any A, B, and A, there is a continuous function f from AB to A, such that I did it again. Okay. 0, 1. 0, 1. Okay. Such that f of 0 is equal to a, f of 1 is equal to b. Literally what that picture has, this is the path or image. What I plotted, that curve, is a path or image, so it's not the graph. And there's really, it's hard to visualize as it is. Even in dimension 3, like on the right, it's hard enough to visualize graphs or functions. And so you at some point you switch to visualizing images rather than graphs. So that curve is the graph, and if you connect any 2 points with by a curve, that set is called path connected. So for example, it's very natural. So for example, square or that square. So full empty square, not empty square, they're all path connected, and this is path connected, and figure 8 is path connected. This is path connected to like this. So even though these 2 pieces have only 1 point in common, it is path connected. Anything that seems to be made of 2 pieces is not path connected. Like this. So not path connected. Because why? I cannot get, this is my point A, this is point B. I cannot get from point A to point B with a curve. Okay, so these examples are all Euclidean. So metric spaces that we pick are nothing exotic, but rather the one that you see in calculus 1 to 3. Okay, there are exotic examples even in Euclidean topology. And where you have this kind, you have something that is not entirely predictable. An example is a comb. A comb like this. So this is a comb, and it has a weird structure. It has the teeth of the same height, but there are more and more of them as I move to the left. Okay, so I don't want to plot all of them, but you can imagine that they continue on. And then, okay, so it doesn't matter how many I've got. I have these, so I repeat these more and more, like a convergent sequence. So once again, teeth are of the same height, and they're getting closer and closer to each other. This is 0 and 1, and they keep going all the way towards 0, but there is no, the last one is not included. Okay, so far this is path connected. Right? So any 2 points can be connected by a curve. Okay? So how do I make it disconnected? And that is I add an extra point. So if this is a comb, I add a fly. Where? Right here. Okay, so where fly is at 0, 1. Okay? So even though I can stay on the comb and get as close as I like to the fly, there is no path to it. Okay, so that is the idea of continuity that kind of have a different flavor from what you're used to in calculus. And path connectedness implicitly appears in many places, in calculus 3 especially, and then but if you want to pursue in a more abstract way, then this is kind of examples you might have to face. So once again, comb, path connected. If you add 1 extra point, it is, even though think about the distance. Think about the distance between the fly and the comb on the plane. What's the distance? So it goes to 0. So this point is 0, 1. This one. So the height is 1. The width is 1, and there are infinitely many teeth. So like what is it? 1 over n. 1 over n. So the bottom is 1 over n 0, or rather 1 over n 0. And the top is 1 over n 1. Okay, so that is these are my 2 teeth. of the cone.
So the distance from the fly comes to be like 0?
It is like 0, right? So because it's not literally 0, but indeed well, there will be a sequence of points, the tips, for example, the tips of the teeth, the distance to which will converge to 0, right? So these are the points, as a matter of fact. So in that sense, the distance from the fly to the comb is 0, and yet you cannot get to it by path, and so you will end up with a set that is not path connected. Okay, so all right. So intermediate value theorem. We'll get back to that because connectivity certainly is the most important topological concept. Even more important, I suppose, than continuity. Even though the way we define path connectedness, as you can see, we define it through continuity. Okay, so not vice versa. And then there's one more theorem. I just want to mention that there is one more theorem from Calculus 1. Once again, entirely about continuous functions. Intermediate value theorem, there is one more. So once again, Calc 1. I will give you the name, just what's the first word?
Mean?
What?
Mean?
No. The mean value, once again, is about the derivative. And we're not doing derivatives.
Absolute.
Not absolute, no. Oh, absolute, what do you mean by absolute? Well, maybe you have something idea in mind, you just don't remember the right word. Well, extreme value, that's right. The extreme value theorem, which I'm not going to state the whole thing, but you might remember that a function defined an interval AB, which is happens to be finite and closed, then it attains its maximum value. So a continuous function. On bounded closed interval, such as AB, inclusive, right, attains its maximum minimum values. In other words, for attains is reaches. Okay, so there is an actual value like this. This is, well, that's not the right one, but this happens to be the maximum for the picture that I made up, and this happens to be the minimum. So if you miss, and that's once again a topological issue, if you miss B, and it's not included, so in other words, the interval is not closed anymore, then the theorem is wrong. Does this sounds familiar? So not only the function has to be continuous, but also the interval has to be both bounded and closed, because if it's not closed, as you can see, it fails. The theorem fails. Or even if the interval is closed, but if it's infinite, once again, it's not true anymore. It might go like this, on and on. So once again, no. So boundedness and closeness of the set is also required in addition to the continuity. And you can certainly think of how a function that's not continuous once again fails to satisfy the like that. Fails to satisfy the theorem. Okay, so once again, maximum is not reached. So the maximum value is here. This is maximum, but it's not reached. Okay, so here, same story. Maximum, this is maximum not reached, maximum not reached. And this one also can have maximum, but if I plot it better, like this maybe, just to make the point clearer, maybe like this. Okay, so then what if it's kind of asymptote here? So then once again there's a maximum, and once again it's not reached. Okay, so then three conditions here, and that's how we take theorems apart. We look at the restrictions, and we gotta make sure, in addition to proof of the theorem, we make sure that we don't require too much. And so we try to see that if I drop continuity, is the theorem still correct? No. If I drop closeness, is it still correct? No. And these are the three examples that demonstrate why all of the requirements are necessary, at least, even though you might try to weaken them all together, but one by one you cannot drop them. Okay, so continuity, closed, bounded, interval, bounded. What?
What's the third one?
Bounded. Bounded, closed. In what order? Continuous 1, closed 2, and bounded 3. Okay?
Okay, but why is that not true? Like,
Over here,
yeah.
well, if it has an asymptote, horizontal asymptote, then that value is the maximum. The technical term is the supremum, or the least upper bound. Okay, so once again, that value is not reached. So it will approaching it, just like in the other pictures, it's approaching the value but never reaches it. Okay, so once again, if we have time, we'll review this. But I actually want to go back to what we have accomplished and what we are more or less finished with, and that is our the metric space. We have only one theorem about metric spaces. But I feel that we could actually see more metric spaces now, more examples of metric spaces, even though we have only one theorem available. But there are metric spaces that are really really interesting, and they go beyond what we have seen. So to refresh your memory, the metric spaces that we have seen are the hard and the hard, then easy, R2. Rn, okay, and on, all dimensions. Then subsets of a metric, subset of a metric space is a metric space that deserves a separate theorem, I suppose. Then what else? So these are Euclidean. So they all have Euclidean metrics. The non-Euclidean could be, say, taxicab metric. Another metric. Then what else did we have? We have all kinds of surfaces, curves and surfaces. Circles, so how you measure distances on circles or on the sphere, such as the globe. And finally, and then weighted graphs. Well, there is one more class of metric spaces that is really important, is function spaces. Meaning simply that its elements are functions. So because metric spaces are nothing but they can be created on any set of any nature. The nature of the elements doesn't matter. So all of these have pretty much the same. They have some how should I put it? Something geographical about it. There's some kind of space of locations, right? So Euclidean spaces, even n-dimensional space, you can get used to the idea that they describe some kind of a n-dimensional universe. Okay, and then you might measure distances in different ways, but there is some underlying their locations. But there are also function spaces where the elements are functions. Okay, so in fact, well, suppose, well, this is a typical example. CAB is the set of all continuous functions. Y continuous we'll see shortly. F from AB to R. So functions themselves are easy, but when you put them together in one place, they constitute quite a big thing. altogether. That's what they form. So continuous functions defined on an interval. Okay. So all right. So then the question is, if you want to approach it in a kind of a heuristic way, then how do you measure a distance between two functions? So what is the meaning? Well, just plot two functions, interval a, b here. Okay, I plot two functions, y equal f of x, y equal g of x. What's the meaning? Well, how do you measure that they're close to each other? Before we get to metric spaces, are these close to each other, and you plot two different ones? Are they close to each other? Then that. How close are these two to each other?
So 2 points, they are each other.
They are equal to each other at 2 points, right? So, but they are not the same. Remember, and then we already have an idea that if we want to have metric space, and we do, then the distance cannot be 0 unless it is the same element. So these are two different functions. So the distance should not be equal to 0 at the very least. So I would require d of g not equal to 0 because they are two different functions. Okay, so the fact that they have points in common, well, I guess maybe not that important. Anything else you can think of? Well, you might, I'm not making this up, you also saw some of that in Calculus 2.
Squeeze through?
Kind of, I suppose it is related, but I want you to, do you remember sequences of functions in Calculus 2? Sequences of functions? What about series? Power series? Taylor series? Okay, so there's a Taylor series. A function might have, if it is well behaved, it has a Taylor series. But what's so good? What is the point of a Taylor series? What is the point of the Taylor series or a function?
To estimate the area of the curve?
No, not estimate. It is. You can use it to estimate the function itself, to approximate the function. So remember, in Calculus 1, you did linear approximations, right? And then in Calculus 2, you did quadratic, cubic approximation. Together, if you keep going, you'll get Taylor polynomials and Taylor series. So then, what we're talking about is that if you have a Taylor series, Taylor polynomials, they will converge to the function. So if you, like I said, you have a function and you create a Taylor series or Taylor polynomials of f, then it only makes sense if those series or the sequence of polynomials approximates the function. Okay, remember Taylor polynomials are polynomials, so they are easiest functions to evaluate. So we're replacing some complicated function with its series. And if you truncate the series, you'll get a polynomial, and those polynomials approximate your function. So if you cannot compute a function, you can do that always with its Taylor series. So that's the meaning of linear approximation and beyond. And that's how you, for example, might compute trigonometric functions without actually doing literal trigonometry. Okay, so how do I compute sine? Well, I have a series for sine. You might remember what it is. That's cosine. Okay, and then so if it has infinitely many terms, but so certainly computer is not going to do infinitely many, but it might do 100 terms, and it will give you a very good approximation of the values. Okay, so how do we describe it in a very concise way? That's how the Taylor polynomials converge to the function. To converge, then you already know we're talking about convergence of sequences in metric spaces. And it works out, we already had a theory about that, it only works out if we are able to measure distances between those elements. And in this particular case, these elements are functions, so we need to figure out how to measure distances between functions. Well, let me give you a hint. Well, let me give you a different hint, actually. How about this? What if one of the functions, say g, is in fact, if it is a zero function? Then what? That should sort of help us. Okay, this is my g function. So this might be too complicated, but how about this? This is my g. So we just want to measure the distance from my function to zero. Any thoughts about that? So these are, if it was a number, it would be easy. Just the absolute value of a number would be, that's what we know about it. If you're talking about the real numbers and you need to evaluate the size of a number, you just take the absolute value of that number, okay? And now we have infinitely many of them like this, lined up. I say one of them is more important than others. This one. This one. Why is it important? What's so special about this point that I picked?
The maximum energy.
It is the maximum. It is the maximum of. It is the maximum, not minimum, but maximum of the distance of the function to the x-axis. Okay, so then I'd say d fg in this particular d when g is equal to 0 is maximum f of x with x between a and b. Why does this make sense? By what makes sense, I mean the idea of using the maximum. But what I'm asking actually not why it makes sense, but why is it well defined?
Derivative equals 0?
What?
Is the derivative of the function equals 0?
No. There's the function is continuous. There's no differentiability. But this still makes sense because of what we just discussed not a long time ago, just today. It's well defined because of a certain theorem, extreme value theorem. So you cannot just say let it be maximum for any function, but since we assume that the function is continuous, that the maximum makes sense, and we can pick that number as the distance. Except, well, one thing I should have added here, we're gonna need the absolute value. Okay, so if the function is negative, you should still be able to compute that. So anyway, and then in general, you just subtract. So distance between f and g is equal to the maximum x run between a and b, f of x minus g of x. Okay? So in other words, we take these distances and pick the largest one. And once again, it makes sense. F continues, G continues. The difference still continues. I compose it with the absolute value, which is also continuous, producing once again a continuous function. And then that's the whole thing is continuous. It is continuous, so it will reach its value somewhere, as I try to suggest over here, that there is some kind of C over there. So this thing is actually is equal to f of c, the absolute value of f of c. At some point, it reaches its largest value. So that's how we measure distances. Well, there are other ways to measure distances between functions, but this is number one, and especially it works for continuous functions, and it is what you are using implicitly when you do Taylor series or the power series approximation of functions. That's how you measure distances, and in that sense, we have this convergence over here. So according to this distance, we have convergence of the Taylor polynomials to the function that they're supposed to approximate. In fact, this is the meaning of the approximation. So if you want to say that, Taylor polynomial, the sequence approximates, that's a loose language, approximates f, what does it mean? That Tn converges to f and then you have to explain in what sense there is a convergence in this space CAB. Okay? So that's the metric. Okay, so that certainly deserves more discussion, that metric space. There's another way to measure distances between functions. Look at that at the top. I suggested that these distances matter, but in other ways to integrate. Another way to integrate is, I wouldn't say it's a better way, but it is also a good way to measure distances between functions that don't even have to be continuous. They could be just integrable. Right. Yeah. Okay, so we'll just resume